Lesson 3. The concept of ship stability. Stability is the ability of a vessel, taken out of equilibrium, under the influence of external forces, to return to it again, upon termination of this effect. From the nature of the affect, static and dynamic stability are distinguished. On the graph, dynamics are shown in red, statics in blue. It can be seen that the dynamic moment is more rapid in time. Statics differs from dynamics, the absence of inertia forces and water friction resistance. Stability at small angles of heel, up to 15 degrees, is called initial stability and is different from stability at large heeling, where slightly different rules apply. 3.1 Metacenter and stability limit. To begin with, let's deal with the metacenter, point M. Other points G and B, I hope, are clear. See the last lesson. In the theory of vessel stability, there is a concept of three metacenters: initial metacenter, true and imaginary. I will consider two of them. The true metacenter is the point M1 and the imaginary one is M, without an index, and the initial metacenter is not so important and is out of our interest. Let us consider the projection of the midsection of a ship afloat with good positive buoyancy. We heel the vessel by a virtual heeling static moment to the right and observe the behavior of point M1, the true metacenter, and point M, the imaginary metacenter. With initial stability 12-15 degrees, these 2 points practically coincide. Increasing the heel, more than 15 degrees, the true metacenter M1 begins its downward migration along a curve called the evolute and then continues its slide down the direction of the support force. At the same time, the imaginary metacenter, point M, remains motionless for a long time, which is what makes it convenient. That is why this imaginary metacenter appears on all diagrams and drawings and is used in all practical calculations. Therefore, I remove the true metacenter M1 from the animation and leave the point M on the screen, the imaginary metacenter. In the future, it is simply referred to as the metacenter, denoted by the letter M, without any index. Let me remind you that it is the point of intersection of the guiding support force B with the center plane of the ship. Let's play the ship's virtually heeling until it capsizes. The metacenter will be stationary up to a certain angle of heel. In this example, it is about 27 degrees when the deck entered the water. The metacenter, which until this moment was not mobile, will begin its movement down along the z-axis. The ship begins to lose its stability. The process will accelerate after the exit of our left shoulder from the water, that is, when the immersed volume of the hull begins to change significantly and the center of buoyancy, CB, begins to move back, to the left. When the metacenter reaches the center of gravity, CG, a position of indifferent equilibrium sets in. Here it is a heel of about 75 degrees. The ship is indifferent, according to the principle, we were pushed, we fell, we were raised, we went. Therefore, at the slightest increase in the heeling moment, the metacenter will be below the CG and a couple of forces will already help roll over. The ship is doomed. 3.2 The position of the metacenter M and the center of gravity G. From the geometry of the figure on the screen, it can be seen that the value of the metacentric height depends on the position of the points M and G. So, the position of the metacenter M depends to a greater extent on the shape of the ship's hull. The decisive role is played by the width of the vessel, as well as the height of the side and draft. The figure shows two vessels with different widths, but with the same displacement. One is long and narrow, the other is wide, but short. The list for both is set the same. Obviously, to heel a wide one, it will take more effort than a narrow one. With the same draft, they have different volumes underwater, so different center of buoyancy movements, respectively, and metacenters are located at different heights. It is obvious that the metacenter of the wide vessel is located higher. The higher the metacenter, with the same coordinates kg, the greater the metacentric height gm, which means it is more stable. This can also be seen from the trapezoidal volume entering and exiting the water, and it is larger for a wide vessel. Consequently, the moving of the sea is greater, which confirms the above. I state without any calculations that a tug or supplier is more stable than any cargo vessel. A heavy lifter does not count. The height of the center of gravity, g, depends on your load condition, therefore, I'll get ahead of myself and say how you load, so you swim. There is a simple rule: heavy cargo down, light load up. More on this in later lessons. (3.3) Stability arm GZ. Again the projection of the midsection. Vessel straight with positive buoyancy. The forces are balanced G equals B, according to Archimedes. Force G is the weight displacement, D, we have. Force G equals displacement, D and equals gamma V, formula 3.1. Where V is volume displacement. Gamma is the density of the water. Heeling to the right is played again. When the ship is heeling, center of gravity, point G, does not change its coordinates, but center of buoyancy, point B shifts, according to the displacement of the submerged volume, is essentially its geometric center. Between a pair of forces, equal and oppositely directed, a arm GZ arises, the shortest distance between the guides of these forces, which is called the arm of static stability and is another of the 8 most important stability criteria. A pair of forces and an arm form a moment tending to return the ship to a straight position. This moment is called restoring. Moment equals arm GZ multiplied by weight displacement, D, formula 3.2. This restoring moment will return the ship to a straight position when the listing stops. (3.4) Metacentric height GM and metacentric stability formula. Let's play the heeling again and analyze the right-angled triangle at the metacenter. The hypotenuse is the metacentric height GM, and the static stability arm GZ is the leg. The angle theta opposite to this leg is the heeling angle. The dependence of the static arm GZ on the bank angle theta is obvious in formula. GZ equals GM multiplied by the sine of theta, formula 3.3. Where theta is angle of heel in radians, degrees divided by 57.3. If we transform formula 3.2 by inserting formula 3.3 into it, we obtain the desired formula 3.4. The restoring moment is equal to the product of the weight displacement times the metacentric height and the sine of the heel angle. This equality, 3.4, is known as the metacentric stability formula. Thus, the values that, for a given displacement d, affect the value of the restoring moment m, those, on the ship's stability are the static arm GZ and the metacentric height GM. These values are included in the stability criteria of both the IMO, International Maritime Organization, also the Russian Maritime Register of Shipping. Pay attention to the metacentric radius r, which is the radius, only on small heels, less than 15 degrees. With large heels, as a result of large changes in the submerged part of the hull, the movements of points B occur along a curve different from the arc of a circle with this radius, therefore formula 3.4 is used only for initial stability, up to 15 degrees. Resume. 1. Static and dynamic stability are distinguished from the nature of the effect. Statics differs from dynamics, slowness, and the absence of inertia forces and water resistance. 2. Stability at small angles of heel, up to 1/5 degree, is different from stability at large heels and is called initial stability, in which other rullies apply. 3. Equals d times gm times sin, tm, metacentric formula of stability and is valid only for initial stability, up to a roll of 15 degrees, if applied further, large deviations arise. 4. The metacentric height GM and the static stability arm GZ are the most important criteria for the ship's stability, values of which are included in the requirements of the IMO and the Russian Maritime Register of Shipping. In practice, having made the first calculations and having received the value of kgc or gmc, one can immediately draw the first conclusions on stability and understand whether to move further in the calculations or it is necessary to redistribute the load.